In this one, we can talk about one of the very important technique, what we call numerical integration, because there are certain integrals which are impossible to evaluate. For example, if you look at the integral e to the x squared dx, you cannot integrate this one exactly. So there are a lot of other integrals that you cannot integrate exactly, but these integrals appear everywhere in engineering and other applications. So that means there should be a way to approximate those integrals. So then we have this technique what we call numerical integration or the approximation. So let's talk about that a little bit. So what we're gonna do is a numerical integration. So numerical integration is a technique that you can approximate certain integrals that you cannot evaluate. Um, Most of the integrals that we find in nature, like, it's difficult to integrate, so we need these kind of techniques. So how we do it, we can talk about three different techniques. What The first one is what we call the midpoint rule. That means we can approximate the functions at the midpoints. Um, and then the next one is what we call the trapezoidal rule, and then we also have the Simpson rule. So let's talk about one by one. Um, so let's start with the midpoint rule. So let's say you have a function which is given in an interval a b, which is a nice continuous function. So what's the midpoint rule does is, so let's say first we're gonna they have the first point is starting point we normally call x naught, and the end point we normally call xn, and then what we normally do is we're going to divide this into equal parts. So we're going to divide this into equal subintervals. The gap of one such subinterval is what we call delta x. So delta x is simply given by b minus a, that's the length of the interval, divided by number of parts. So this is a formula that we need later. So delta x, that means the gap, is simply b minus a over n. Now what we're gonna do, we're gonna approximate each uh, the goal is to find the area below the curve. So what we're gonna do, we find a typical value. The typical value is the value at the midpoint of each interval. So we're gonna use this one as a representative value and consider that as the area. So we simply gonna evaluate this area. So we evaluate this area using the middle point of the interval. So do the same thing. So we're going to pick the midpoint. That's the midpoint of this interval, and pick that as a representative value and calculate the area below the interval. So we can do that for each and every interval. So we get that, and for this, so that's the middle value, and then we can get this. So the gap is we call delta x. So we have that, and then what we can do, we can use star notation. We can start with x naught, and then we have x1, x2, like that, and the last one, this is x n minus 1, and then we just keep doing it. So now what we can do, we're gonna find the midpoint. We need a notation for that. So for the midpoint, what we normally call x1 bar, we will call x1 bar. That's the midpoint here, and like that the midpoint here is we call x2 bar, like that. So that means in this case xi bar, the midpoint is simply half. What we can do, you can add the two and divide. So in this case what we have is we have xi minus 1, that's the first one, and then one before it, and xi. So take the half of it. So that's how you calculate those average values or the midpoints. You're gonna add the two and divide by 2, and then after that we have this formula, and also we can have the ith node. What we call the next one is the ith node. So ith node is normally, it is starting with a plus I times one such gap. So this gonna give you the ith node, and we use those nodes to calculate the midpoints, and then we have this midpoint rule. So let's put this up there, and then this is the number line that we have. So we have a, which we normally call x naught, and the ending value xb, xn, which is b. So what we can do, we have x1, x2, like that, and then at the end we have xn minus 1. These are all equal width. So and the first middle point we normally write as x1 bar. second middle point you write x2 bar like that. So this is the xn bar like that. So each node is simply given by the a plus I times one such gap. That's one formula. And then if you need the ith node, middle point, it is 1/2. You can add the two neighboring ones. That means xi minus 1 plus xi. So those are the formulas we need to, so that's the middle point for this one. So then we can write the middle point like this. So that means a to b fx dx, which is simply the area of the rectangle. That means delta x, which is the gap. What you need to do is simply add the heights. So that means fx1 bar plus fx2 bar like that. We can add all such heights. So that means fxn bar. So those are the heights. So that is the formula for the midpoint rule. It's very simple. You can add all those heights. So delta x times height. So and then these are all midpoints in each interval. These are the midpoints. So midpoints. And we do a problem, then it will be very clear. So that's what we call the midpoint rule. So it's a very simple rule. You evaluate the function at the midpoints. Okay? Function at the midpoints xn bar, not at the node point, not the node points, but the midpoints. Okay? Good. So let's write the formula for the trapezoidal rule. So let's look at the node points. So we have the starting one we normally call x naught. Also this is A, and the last one we call B. This normally we write as xn. So we normally call this is xn. This is B value. What we're going to do, we're going to divide into equal parts. So these are the equal parts, equal what we call subintervals. So this is x1, x2, and this is xn minus 1, xn. So what we have is the gap of two such subinterval. This is delta x, which is b minus a divided by n, and each node you can calculate from a plus I times the delta x. So those are the formulas. So let's write the two formulas. First write the trapezoidal rule. So trapezoidal trapezoidal rule, so which is simply given by, so it is a to b fx dx is approximately equal to trapezoidal n, so which is delta x over 2, and then we have so the format is 1 2 2 2 2 1. So that means we're going to start with the first one, which is fx naught, and then every other node you're going to multiply by 2. So it's going to go like that, going to go like that, and at the end it's 2 fxn minus 1 plus fxn. So that's the rule for the trapezoidal one. So we have all internal one have 2 everywhere. The first one, the last one has a 1 as coefficient, and then we have the Simpson rule. So Simpson rule. So in the Simpson rule, no much changes. So what's gonna happen? This one we're gonna divide by, this is called Sn. We can divide by 3. We can divide by 3. So the midpoint rule divide by 1, trapezoidal rule divide by 2, Simpson divide by 3. So what's gonna happen is here the format is 1 4 2 4 2 4 like that, and then at the end 2 4 1. So that's the format of the node values. So that means f x naught, each odd nodes multiply by 4. Sorry, 4 f x1 2 f x2 like that. So that's what happened. So at the end it's going to end like 4 f x n minus 1 plus 4xn. So that's how it's end. The only restriction here is n has to be even when you use the Simpson rule. So those are the two rules. So this is a trapezoidal rule, which has 1 2 2 2 1 format, and then we have the Simpson rule, which has 1 4 2 4 2 4 1 format. So good. Now what we can do is we can use this in a problem and see how it works. So let's do this problem. So example, let's say approximate the integral 1 to 4 1 over x dx with n equals 6 using. So let's do one by one. So let's start with the midpoint rule. So we're going to go with the midpoint rule. So to use the midpoint, we need to evaluate the node point. So we're going to start with 1, that's the starting value, which is x naught. And then the last one is 4, which is x. You can see there are 6, so it's x6. So there are other values. So and then we have so x1, x2, and then x3, x4, x5, and x6. So the starting value is 1, and then 2, and then 3, and 4. So what? So this is 1.5, 2.5, 3.5. It's a good idea to like mark them, and then we need to find the midpoints. So for example, we can calculate x1 bar. So this is x1 bar according to the notation. So x1 bar is simply 1/2. So you can see you add the two around, so 1 plus 1.5, so that means you get 1.25. Similarly, x2 bar, which is 1/2, add the two around, 1.5 plus 2, so you get 3.5 half, so it's 1.75. So like that. So you can calculate all those nodes in that way, and then what we can do, and the gap. So you can see the gap is yeah, so we should have calculated that first. So delta x, so you can calculate the gap, so which is delta x, which is b minus a over 2, so b minus a over n. So in this case 4 minus 1 over 6, so which is 0.5, so which is 0.5. So that is one reason why every time we jump with 0.5. Okay, so that's the delta x. So one such delta x is 0.5. Good. Now we have the nodes, so we can write the formula. So we know that, so 1 to 4 1 over x dx, which is approximately equals to m6 as a midpoint rule, which is delta x times what we can do, we're gonna evaluate at the midpoint, so x f1 bar and then f x2 bar, like that. So the last one is f6 bar. So let's plug in that. So delta x is in this case 0.5, and then go to the function plugin. So it is 1 over 1.25. So that's the first midpoint. Yeah, so that one, that's the first midpoint, 1.25, and then 1, and then 1 over 1.75, that's the second midpoint, and then 1 over 2.25, 1 over 2.5, 2.75, 1 over 2.75. These are not the node point, these are the midpoints. So 1 over 3.25, 1 over 3.75 plus 1 over 4. Yeah, that's the last one actually. So those are the 6 midpoints, and then you can use a calculator. So if you use a calculator, and you can see that this is roughly equal to 1.3769 to 4 decimal places. So that's how you use the midpoint rule. What we did was we calculate the midpoint for each interval. Now let's do the trapezoidal rule. So B, so we can use the trapezoidal rule. So if you use the trapezoidal rule, it's pretty much the same. The format is 1, 2, 2, 2 like that, and then 1. We can evaluate at the node points now. So delta x is the same. Delta x is the same. So which is 4 minus 1 over 6, which is 0.5. So we can start with x naught and then x1, x2 like that, x6, and then each gap is so we can start with 1 and then 1.5, 2 like that. So we end up with 4.0. So every time you jump with 0.5, so that means your formula you can write. So the format is 1, 2, 2, 2, 1. That's the format of the trapezoidal rule. So we can write it now. So 1, 2, 4, 1 over x dx approximately equal to the trapezoidal 6, which is delta x over 2. That's the formula. And then fx naught plus 2fx1 plus 2fx3 like that, and then the last one is fx6. So now we can plug in. So we're going to get 0.5 over 2. So we're going to get f evaluate at the first node point, so 1.0, and then 2 times f 1.5 and 2 times f 2.0, and then 2 times f 2.5, and then 2 times f 3.0, 2 times f 3.5 plus f 4.0. So that's the formula, and then we can plug in it. So you're gonna get this 1 over 1.1 plus 2 over 1.5, 2 over 2.0, 2 over 2.5, 2 over 3.0, 2 over 3.5, and 1 over 4.0. So you can see on first and the last one has a 1, everything else has a 2 as the coefficient. And if you use a calculator, you can see that you're going to get 1.0653. And then we can use the Simpson rule. So we're going to get that from the Simpson rule. So node points are the same as the trapezoidal rule. The format is 1, 4, 2, 4 like that, 4, 1. That's the end. So the rule is 1 to 4, 1 over x dx, which is approximately equals to S6, which is delta x over 3. And then the formula is fx naught, the first one, and the all odd one you multiply by 4, and all the even you multiply by 2. So it's going to go like that for fx3. So we have, and then 2fx4, 4fx5 plus fx6. So now we're gonna plug in the values. Once you plug in the values, you're gonna get 0.5 over 3 now. So 1 over 1, and then 4 over 1.5, 2 over 2.0, 4 over 2.5, 5, not 5, 2 over 3.0, 4 over 3.5, 1 over 4.0. So if you use a calculator, you end up getting 1.3876. So let's try to find the exact value, because this is something that you can do. So exact value is the integral 1 to 4 1 over x dx, which is very easy to integrate. This is natural log x 4 1, which is ln 4 minus ln 1. Ln 1 is 0, so which is ln 4. Roughly this is equals to 1.3863, and you can see that the Simpson rule value matched very well. So which is correct up to two decimal places, and also if you round it you get correct up to 3 decimal places. But the trapezoidal rule is the worst one, that has a value which is very off of this value. Midpoint rule is in between the two, so the best one is the Simpson rule. So these are some of the examples that you can do with those three numerical approximations.